We all know Tesla's development of the full self-driving feature and the respective attempts by some of the other players that are already in that game, such as Nvidia and Waymo. But we also know new ones, such as the big German car manufacturers like Mercedes and BMW. But where such autonomous navigation is also to be found and already used is in much simpler industrial settings. On the one hand, we have autonomous robotic arms, but also car-like robots. In this video, I'll show you some fundamental research and development for those autonomously navigating vehicles, going from training and tuning the models for different robot types to their deployment. For those of you who don't know, I'm a computer science and engineering student, and for a while now I've been working on a project that addresses exactly that problem. So I thought it might be cool to see on a high level how such models are trained using deep reinforcement learning and how to tune those models for different input types and different robot types and just how to increase their performance. First of all, on a high level, what is deep reinforcement learning? We have our actor, which in literature is referred to as an agent. This little guy can be anything from a little robot that can pretty much only drive around, over to bigger ones that have a face and arms, to our favorite car that can transport humans safely through traffic. This agent, in a sense, has some sort of vision, be it an actual camera or multiple cameras, one or multiple LiDAR sensors, or even sound. Since with my project we pretty much only work with LiDAR and it's the easiest method, we'll stick to that for this video. Now with this vision, at each discrete time step the agent makes observations, in our case the data of the LiDAR sensor, which tells the robot how far away the objects around it are. Those observations are then the input for our neural network that then returns some action. The agent makes one step by taking the action, and the next set of observations are gathered, fed into the neural network, and a new optimal action is predicted. Then comes the next new observation, and so on and so forth. For that, we let the agent train for millions of time steps in a simulated environment. Commonly, this training is performed in a 2D environment, because our LiDAR sensors detect the surroundings basically in 2D, and it is computationally a lot, and I mean a lot, less heavy. To evaluate the performance, we then deploy the trained model in a realistic 3D simulation or directly onto the real robot. This means we need to choose a robot that we want to train, since each robot does not only have a different footprint, but also different laser scan definitions. Not all have a 360-degree view, and the maximum range of this laser can also differ. Additionally, each robot can have a different maximum linear and rotational speed, or even different degrees of freedom, but we'll just ignore that one for this video. So, let's choose our fighters for this video. In one corner we have the 0.226 meter wide Turtlebot 3 Burger with a staggering 360-degree view with a 1-degree resolution and maximum laser range of 3.5 meters. He really stands up to his name and has a maximum linear velocity of 0.22 meters per second and a maximum rotational speed of 2.84 radians per second. In the other corner we have the absolute unit called Jackal with his 0.534 meters diameter. He has a blind spot behind him with his only 270-degree view, but don't let him fool you. In those 270 degrees he provides 720 entries and has an insane maximum laser range of 30 meters. Compare that to the 360 entries with a maximum of 3.5 meters of the Turtlebot. But he doesn't stop there. His maximum linear speed is 2.0 meters per second and he can rotate with astronomical 4.0 radians per second. Will he be able to control himself with that speed? Now that they were introduced, we of course have those models defined in our 2D environment. The Turtlebot 3 is a nice little circle and the Jackal is this polygon shape. To perform the training, we let the agent initially take random actions, following the scheme we have discussed before. We have an observation on which the neural network predicts an action, and then we enter a new state with a new set of observations, which then predicts a new action, etc. But to tell the agent which action was good and which was bad, we define rewards. For example, each step the agent takes, we look at the scan data and look if some value is smaller than our radius plus some minor buffer. In that case, we have a collision. If everything is fine, we can, for example, give no punishment, or just 0 points. But if we do have such a case of a collision, we can give, for example, minus 10 points. And this is one of the main tuning tools for training a better agent or invoking a specific behavior. We can change the actual value from minus 10 to, for example, only minus 5 if we want the agent to drive more risky. Now that I'm thinking about it, additionally, we need to give rewards for the agent driving towards and actually reaching the desired goal, which existence the agent in fact doesn't even know of yet. The agent, or to be precise, the neural network, can only react to the input we provided. Therefore, only the scan data isn't enough. So we extend our input observation space by, for example, the distance and angle of our agent to the goal. This observation is pretty much already enough to train a fairly good agent. By adding more complex rewards and tuning the actual penalty values, we can really get going. How those rewards are actually used to train the weights of the neural network is perhaps not for this video. But what we are going to look at is how this training can look like or can, for example, be designed. We have different stages with different difficulties, like in video games where you have increasingly more difficult levels. Initially, it of course makes sense to just let the agent perform random actions and train in the easiest environment, an empty world. Once this agent learns to drive better and achieves a certain level of skill, we switch the world to a more complex one with actual dynamic obstacles, until it eventually reaches the most difficult level where we have a lot of dynamic obstacles. Additional fun fact, to speed that up even more, we can let multiple agents, each in their own environment/world, drive around in parallel and then train one network with the rewards of each agent. After training for 10 million time steps, let's look at the performance of the Turtlebot. As I said, he is a literal turtle. He drives very slow, but follows the global path well and drives towards the desired goal. He also has basic obstacle avoidance. Nevertheless, we can see this little zigzag pattern, which is not very efficient and not really what we want. We've been focusing on our Turtlebot for a while now. Let's look at our Jackal, which was trained with the exact same rewards but larger observation space. Since, remember, he provides 720 laser scan entries. He is really fast, especially compared to the Turtlebot 3, but he is also drifting/sliding around a lot. Which is weird since in the 2D simulation for training, it didn't do that. So, why is it bad in 3D then? Well, it's because of the physics. The agent's turns are very fast and abrupt, so it slips away or breaks through. In 2D, those physics are simply not integrated. At this point, we start tuning the rewards, perhaps the observation space or even the action space. For example, we can add a new reward that punishes abrupt change in velocity. This should fix the zigzag problem. But the agent or the neural network can't really know if its new action is a too abrupt change in velocity if it doesn't know the previous reference velocity. So we extend the observation space and include the prior speed of the agent. If we really want to go crazy, we can also extend the action space and allow each robot to also drive backwards. Let's see what would happen. So let's first look at the Jackal and he has completely lost it. He prefers to drive backwards and just spins around like crazy. Now, the Turtlebot 3 was also driving backwards, so we just added a rule that penalizes reverse driving, so that he prefers forward driving. Again, tuned the actual individual reward values, and now we have a pretty good agent. Developing and optimizing a deep reinforcement learning model is a very iterative process that involves a lot of trial and error. For the Jackal, we can, for example, again change the action space and reduce the angular velocity that the model is actually allowed to predict. Or we simply have a pragmatic solution and scale down the velocity that the model predicts when deploying the agent. This pragmatic solution did actually work fairly well, but is of course not the desired one. We here have a pretty well-tuned Jackal. The sliding around that we previously had is actually quite nice for this video. It shows how important it is to have a realistic simulation environment for training and illustrates the gap between simulation and reality. We are continuing to tune the Jackal and also work on training other robots, but this Jackal is just our absolute favorite. His specs are just crazy. I'll perhaps make a follow-up video where I show you how this process has developed and how we have tuned and trained other models for different robots, but also including the Jackal. Additionally, we have also trained all robots in different 2D simulation environments with different neural network architectures and different observation spaces. In one of those cases, the Turtlebot, for example, learned a different mechanism of dealing with dynamic obstacles. Namely, spinning around in one position and praying for the bad guys to go away. It was a lot of work integrating all robots into those different environments and then combining all models into one deployment and evaluation setup with multiple different maps. But the part of tuning the actual DRL models for each robot is a lot of fun, because reinforcement learning can produce very odd behavior. Or your 3D robot models don't really have the right physics and you get something funny like a flying robot. Or you have to be creative yourself to figure out what you can change in the rewards or observations to invoke the behavior you actually want to see. For example, removing the zigzag pattern. And that was it for today. If you have enjoyed this video, found it inspiring to work on something similar yourself, or have learned something new, please don't forget to like. If you want to follow along my journey as a computer science/engineering student, please feel free to subscribe. And if you want to continue watching, up here is a video that you might enjoy. And with that said, as always, thank you very much for watching, and I will see you guys in the next one. Bye!